Hello everyone. We have studied about the motion of a vehicle on a level circular road. And there in the last we had left the discussion at the point where we discussed that more is the friction, more is the velocity of the car on a level circular road. But more is the friction, more is the wear and tear of the tires. So what's the solution? The solution lies here in the banking of roads. So what is a banked road? Have you seen the circular tracks which are used for the racing vehicles? Or in other words, have you seen the racing tracks? You must have seen that the racing tracks are not level. These are elevated on the outer side. So if I say that this is your level road on a circle, this is a part of that level circular road. So every part of that level circular road is elevated like this. So if you look at the cross section on a level road, that is a level line. But if you look at the cross section on a banked circular road, it is like this, right? So what is banking of roads? Banking of roads is raising the outer side of the circular road above the inner side. The raising of the outer side of a circular road above the inner side is called as banking of roads. So if I talk about the angle of banking, so obviously the angle of banking will be the angle which this incline makes. Suppose this is the road, now it is elevated like this. So at every point, if you look at this cross section, so whatever angle it makes with the horizontal, this is called as angle of banking. The angle which the raised road makes with the horizontal on a banked circular road is called angle of banking. Now look at the diagram. Diagram is very much similar. It appears to be similar, but that's a three-dimensional case, so I'll have to draw it in a different way later. So this is your circular road, and let's say this is the banked one. So banked means if you look at the cross section of this road, this will be like this. So I'm drawing a separate diagram where I'll show the cross section of the road. So this is what? This is the cross section of the road. So this is the cross section of the road. Now this is the radius of the path, and our car is moving on this track. So this is our car. Again, these are the tail lights. So since I am drawing here the inclined cross section of the road, so I'll just draw this car here. I have to mark all the forces acting on it. So the first force is the weight acting downwards. Now this friction force is acting parallel to the surface. Friction is acting parallel to the surface. Normal reaction acts normally outward. right? If this is the angle of banking, we know that this will be the angle theta only. So if I want to find the components, here I need to think about the components. See, we have to keep the car on the circular track, and our circular track is everywhere like this. So if I say that the force is along, centripetal force is along the friction force, so the car, if your car is here, the car will fall like this. So we want the car to move on this banked road. So that means there is some force which will hold this car on the central line of the circle. Now this is three-dimensional. So that means instead of finding the components parallel to this, we'll find the component along the horizontal direction which holds the car on the complete circular track along this central line of the circle, or you can say the axis of the circle. So that's why this is a very important point to think, that here we will find the components of this friction along this direction, normal reaction on this along this direction, right? So that means we are considering this as our vertical and this as our horizontal, right? So for simplicity, I'll draw the diagram again. See what all forces are acting here. The mg force is acting this way, normal reaction force is acting this way, and friction force is acting this way, right? I'm considering this as vertical and this direction as horizontal. So I need to find the components of friction and normal reaction along horizontal and vertical, right? So mg ke components I don't require. Now if we look at the angle beta, if this, I need to find this angle or this angle for normal reaction. So it's easy for me to find this angle because these are vertically opposite, right? But I don't need to find the component of mg. So here it will be r cos theta. So this will be r cos theta along this way. Okay. Now for this friction force, I know that this is the angle of banking. So this will be alternate angle. So if this is the alternate angle, so here I can mention for your convenience that this is vertically opposite angle, and this I can say that this is alternate angle. So I can write that this is the component of friction. Sorry, this was r sine theta. This was r sine theta, obviously, right? So this is fs cos theta and fs sine theta, the vertical component of friction. So here again it is messed up, so I can draw another diagram where I can show that this is r cos theta and this is fs sine theta, this is mg, this is r sine theta, and this is fs cos theta. Now look at this. Which forces are holding the car towards the central line? As I told you that this is the car placed over here, right? And this car is held on the circular path by keeping it on the central line. So these two forces are keeping it on the central line of the circular path. So what are these? I have already mentioned here, this is r sine theta and this is f cos theta, right? So what will I write? I'll write the first equation balancing this. So this is r cos theta is equal to fs sine theta plus mg, right? So I can solve it further. R cos theta minus fs sine theta is equal to mg. This is my first equation. Second equation is that these two forces are providing the centripetal force. So here r sine theta and fs cos theta are providing the centripetal force. So this is easy for you now. I can write this expression r sine theta plus fs cos theta is equal to mv square upon r. If I mark this as equation 2, so divide second equation by 1. So that means r sine theta plus fs cos theta is equal to mv square upon r is our second equation. I'm dividing it by first, so that means r cos theta minus fs sine theta, and this is divided by mg. So if we solve it, this will be v square upon rg on right side, r sine theta plus f cos theta upon r cos theta minus is equal to v square upon r g. So if I divide the left numerator and denominator of left hand side by r cos theta, so divide numerator and denominator of left hand side by r cos theta. Let's see what do we get. First we'll write the same. So r sine theta plus f cos theta upon r cos theta minus sine theta is equal to v square upon rg, and we are multiplying by r cos theta. So here it is r cos theta, here it is r cos theta, here also r cos theta, and here also r cos theta. So check out what happens. Now here it is cancelled, here it is cancelled, and this is also cancelled, and we will get sin theta upon cos theta is tan theta plus f upon r is mu upon 1 minus mu tan theta, right? And this is equal to v square upon rg. So if we solve it, we get v square is equal to rg tan theta plus mu s upon 1 minus mu s tan theta. Now v is equal to rg tan theta plus mu s upon 1 minus mu s tan theta, and this is in under root, right? So important points over here are, number 1, even if friction is 0, which is an ideal case. So if friction is 0, then what will be the value of velocity? This will be under root of rg tan theta, because this will be 0, this will be 0, so the result will be under root rg tan theta. Second point, less wear and tear of tires as even less friction may give more speed. Right? Why so? Because here this centripetal force is given by horizontal components of normal reaction, that is r sin theta, and friction. What was the horizontal component for friction in this case? It was F cos theta. Right? So this is all about the banking of roads. I hope you understood the topic. So that's all for now. Have a nice day.